Hello guys, welcome to Geometrics. We'll be presenting the ordinary least squares through Eviews, and we're going to look at what is ordinary least squares. We're going to look at why is it called ordinary least squares and what the OLS actually does. We're going to look at the key assumptions of OLS and a practical example using Eviews. Now, OLS is a standard method to perform linear regression. OLS is also the most common method for finding the best fitting straight line through a scatter plot of data points. So why is it called OLS? First of all, why is it called ordinary? Ordinary implies that the method makes a specific set of standard assumptions about data and errors, such as linearity, no perfect multiple linearity, isogeneity, homoscedasticity, no autocorrelation, and normality, among others. And so least squares means finding the line that results in the smallest possible sum of the squared error. So ordinary least square is the standard basic version, since we have other types of least squares like the weighted least squares and the generalized least squares. So for these standard assumptions, that is why it is called ordinary least squares. And so we're going to look at what OLS actually does. What it does is to draw a potential line with some slope and intercept, and it measures vertical distances from each point to the line. These are called residuals or errors from this point to this point. That gap is called the error. Then it squares each distance to make them all positive and punish large misses. And then it adds up all the squared distances and they adjust the line to make this total squared error as small as possible. Then the line that gives the smallest possible sum of squared errors is the OLS regression line. This is the regression line, and so the ordinary least square calculates BO, which is the intercept, and B1 using formulas that guarantee the smallest possible sum of squared errors, as is what OLS actually does. And what are the key assumptions of the ordinary least squares? We have the linearity, and the true relationship is actually a straight line. No perfect multiple linearity, as the independent variables are not perfectly correlated. Homoscedasticity, there's equal variance of errors across independent variables, so that's X. So no autocorrelation, errors are not correlated with each other. So normality, errors are roughly normally distributed. So we're going to look at a practical example using Eviews. At each step we have to import data to Eviews. Then we click on Quick, and we select Estimate Equation. And we specify the equation, specify using Y, then C is a constant and the X is the independent variable. Then we click OK to estimate, and then we check key assumptions, and then we interpret regression results. Okay, let us bring this up. Okay, let us minimize this. Okay, I've already imported the Excel data to Eviews, so we click on Quick, then Estimate Equation, and then all I can do is to specify the variables to Y, C, and X. But please, before that, we have to make sure that what this entails. Our model is the Y is what family expenditure, the BO is the intercept, the B1 is the slope, and X is the family income. So the Y you see here is family expenditure, and the X is what? Family income. Okay, so let us go back to the steps. You click CX, this is Y. Okay, you click OK. Yes, this is the regression results. We've seen the first one, and let's look at an expanded view of it. Okay, this is the regression results. Having imported Excel data to Eviews, you click on Quick, select Estimate Equation, and we specify equation. So this is the result we've gotten, the exact result we've gotten here. Yeah. And then what is the next step again? Our next step is to check key assumptions. How do we check key assumptions? First of all, our equation is linear, and then we also have to check for equal variance of errors, homoscedasticity. We also have to check for autocorrelation to make sure that there is no autocorrelation. I have to make sure that there is no perfect multicollinearity. I have to check for stability, how stable the model is, and how normal the model is, or how close the variables are, how close are they to being normally distributed. You can see each of these key assumptions and run it in your model. There are videos to show this: the testing for normality in 3 minutes, test for stability in 3 minutes, testing for multicollinearity in 3 minutes, autocorrelation detection test in 3 minutes, heteroscedasticity detection test in 3 minutes. So you can check this at the short videos of my channel. You will see the procedures for checking the key assumptions of the OLS. Once again, check the short videos of the channel to know how to run and check the key assumptions of the OLS. Okay, so we'll now move to our own result and see how we can check for. Let us check for heteroscedasticity. Check for heteroscedasticity in the white. Okay, this one is okay, this is okay. Okay, let's check for normality. Okay, our Jagbera is okay. Our Jagbera is very okay. Okay, let us check for serial correlation. Okay, we can see use that of double Watson. Okay, it's okay. Let us check for stability. Stability test. Okay, yes, it's okay. So like I said, you have to go to the short videos of the channel so that you can see a detailed procedures on how we can carry out the diagnostics, different diagnostics for the model. So, but for this model, when it comes to the diagnosis results, there is equal variance in errors. Normality test shows that the data in the model is compatible with the normal distribution. Also, the autocorrelation test shows that there is no presence of autocorrelation. For the stability, it shows that the model is stable. And for multicollinearity, it's not relevant in this case because it is relevant for a case of multiple regression where we have more than one independent variable, more than one x. Yes, when we have x1, we have x2, then multicollinearity can apply. F test, the overall model is significant at 5%. Yes, 5%. And for the R squared, 95.7% of the variation in independent variables displayed the dependent variable. So that is for this model. So while doing yours, you can also go and see the procedures for doing that by watching these short videos on my channel. Okay, now when it comes to the result, let's see the result. The result shows that the coefficient of x, which is family income, is 0.509091. Yes, this implies that a positive relationship exists between family expenditure and family income. And this relationship is significant at the 5% level. Hence, a 1% increase in family income increases family expenditure by about 51% on average. So the intercept 24.45455 shows the average level of family consumption when family income is 0, which is most times is not possible. So most times intercept is not important at all. So this is just the ordinary least squares, simple to carry out. As far as the assumptions, the diagnosis tests are okay, then your model is okay. Thank you very much.